How you doing? I'm Mr. Rose, and today we're going to continue to talk about rotational motion in angular momentum, otherwise known as twisty force or physics with a twist. So to start, let's revisit what we know. We know that if torque acts on a particle, it's going to get that particle to rotate. We've only really talked about maximum value of torque, meaning I'm applying a force at some distance away where I have some perpendicular distance. I rotate that. I apply a force to that point along some arm. That causes us to twist. We've spoken about that at some 90-degree angle, which is again going to be our maximum. We also know that torque is a vector quantity, which becomes very important. So if my arm, how far away I am from my axis of rotation, gets longer or shorter, or I apply a bigger or smaller force, that's going to affect the amount of torque I have on the object. Also, we would note that just like that door example, when I was pulling on the door, if I am pulling with not a perpendicular force, let's say I'm pulling with a parallel force, wouldn't make any sense. Doors can't open if I'm pulling with a parallel force. So we know that our maximum torque, by definition, happens to be at 90 degrees. And you saw that very easily from opening the door with the doorknob. Our minimum torque, therefore, would be if you're applying a force at 180 or 0 degrees. We'd have zero torque, and that just makes sense intuitively. The reason why it actually makes more sense, I shouldn't say more sense, the reason why it makes sense mathematically is torque is not just R times F. It's not just some distance times a force. Torque happens to be a cross product. So what do I mean by cross product? Well, we've done a dot product before, and remember, a dot product is called a scalar dot product. Now we're talking about torque, which is a vector cross product. So our torque is actually equal to our distance away from center, distance away from that rotation, not the center necessarily, and the force that acts on it and what that angle is in between. So if this is my arm, what that angle is in between my force vector and my axis of rotation. So our cross product, R cross F, is really RF times the sine of the angle in between. Or if I were going to calculate out our entire cross product, that's just A cross B or R cross F. And we're going to get back into that momentarily. So some things about this torque equation that I'd like you to know, or this general format equation, I should say, is our A cross B equals C. First of all, I just have all magnitude, so we know it's easily positive just to start. We know it's the same exact format where torque would be our C, R cross F is is A cross B. In general, my angle is in between my R and my F. It's going to be a smaller angle because we know we have to pick which angles they are. We know the cross product just intuitively, again, anything parallel or at 0 degrees would have a cross product or torque of 0, and then our maximum product would be at 90 degrees, and again, that's because the sine of 90 is 1, the sine of 0 or the sine of 180 is going to be 0. So let's look at an example of this. Now again, torque is a vector, which means I can have it in some I, J, K notation. So if I have a general form of maybe an R and an F, I have vector A, or my R vector, as AX in the I direction, AY in the J direction, AZ in the K direction, and then the same thing for my force, or my B vector here, BX in the I, BY in the J, and BZ in the K. What we're going to do to figure out our answer, our cross product, is we set up a simple matrix. And it's a 3 by 3 matrix where I have A cross B. I have IJK across the very top. That's how I know what I'm solving out in what form. Then I have my vector A and vector B, keeping all of my forms the same. All of my X values go in the I hat column. All of my Y values go in my Y hat column. All of my my Z values go in my K hat column. Now, how do I solve it? And I solve this and I think about it kind of just like algebra. First of all, my general form at the end is always my I quantity minus my J quantity plus my K quantity. Secondly, what I do is I'm starting with my I, so I'm going to look for I. So I pretend it's not there. I cover up that column, meaning I am solving for I. And then what we do is I'm essentially left with this small little 2 by 2 matrix. I then multiply my AY times BZ, so AY BZ minus AZ BY. That would be in my I hat direction. So one more time. I cover up this I hat like it doesn't exist. Just cover it with your hand like piece of paper. Now I'm left with just my J and my K components. I multiply AY times BZ, multiply those two, and then subtract AZ minus BY. That's my I hat direction. Next, I cover up my J column and I do the exact same thing. AX, BZ, multiply those two, minus AZ times BX. That is in, if I covered up this J column, that's in my J hat direction. So I would have my I hat minus my J hat. Last, I'm going to look for K. So that's AX times BY minus AY times BZ. What that looks like put all together, A cross B, there's AB, AX BY, I'm sorry, AY BZ minus AZ BY. And then again, I hat minus J hat plus K hat. That is how I find something in a general vector form. I'm going to leave it in IJK notation. That gives me my vector quantity. Remember, the cross product of the answer is a vector quantity, so I need to leave it in that, or I need to take the square root of it and then give an angle. So here's a real example now, where I have a disk, my analogy for a disk, and that disk is rotating. If I wanted to know the torque on this, I know it's a cross product. Well, I know I'm applying some force to the edge of this disk, and it's at some distance P away, that's point P, so I have my radius, or my axis of rotation, labeled R. I apply a force to the end of that at some angle, so I can extend that out to figure out what my angle is. Now, there are a couple of different ways I can find my direction of torque. Again, it has to have a direction because it's a vector. The first way I'm not a huge fan of, but I'm going to go through it anyway. There are two right-hand rules we're going to go over. The first one is just your fingers go in the direction of R. So here is my cylinder. I'm going to pop it up so we can see it. Take my fingers and put in the direction of R. Now, I can't really get my hand going in that direction unless I stand up. Get my fingers going in the direction of that R, but since it's a circle, it doesn't matter. Coming out from the center. Then I curl my fingers in the direction of motion. So if I look, it's turning that way on my screen. So I'm going to curl my fingers, get that back on the screen, in the direction of motion. Curling my fingers in the direction of motion would give that its rotational velocity. My thumb right now is pointing away from you or out of the screen. And if I flip it back up, my thumbs up is pointing in the direction of the torque. So I know the torque is going perpendicular to this rotational axis. That's how we do it with this right-hand rule. And then notice, if I was doing RF sine theta, there is my angle. Now there's another right-hand rule, and this is the one that I prefer because this works for everything as well. This is my three-finger right-hand rule. I like the three fingers because my three fingers are always set up to be perpendicular. And even if it's not for a problem perpendicular, I can adjust to still get my directions. My general form is always A for my pointer, B for my middle finger, and C for my thumb. So here I have R, F, and my torque. And if I go back to that example, I have my R is my finger. R is my radius pointing out. Now again, I would be knowing from the problem the direction of this rotation, and that's kind of key. How am I going to make this rotate in that counterclockwise direction? Well, counterclockwise is positive. So I have my rotation that way, and my force vector is pushing it up. Now again, we can see that my fingers aren't really perpendicular, but that's still going to make it turn. So I stick my thumb out, and I have that in agreement again. My torque is going in the vertical direction. So those are two right-hand rules how I find my direction because, again, this happens to be a vector. Now here I have a worked out example. What do I do with all of this? I have a worked out example of three forces at point R. R is given at some distance away. I have my three forces, and R is given as a factor of R cosine theta in the I hat. There is no J hat direction, R sine theta in the K hat direction. I know I have a force of 2, 2, and I lost the 2, sorry, 2 in the I, 2 in the K, 2 in the J, and they gave me R equals 3. The very first thing I do, I want to know what my value of R is. So I throw in my value for theta, my value for R. I know R in the X direction is 1.5. I know R in the Z direction is 2.6. I know I have no R in the Y direction, so I have my R vector of 1.5 I hat plus 0 J hat plus 2.6 K hat. Now my torque, R cross F. If I want to know what is the torque in vector notation, I set up my matrix. IJK, 1.5, 0, 2.6. That is my R. I set up my force, 2, 2, and 2. And just like we saw a couple of slides ago, I cover up my I, 0 times 2, there's 0 times 2, minus 2.6 times 2, minus 2.6 times 2, in the I hat direction, because that's what I covered up. I do the exact same process, cover up the J, 1.5 times 2, minus 2.6 times 2, that's in my J hat. Last, cover up the K, we have the same thing. I can set up the whole thing, and I say now torque is equal to negative 5.2 I plus 2.2 J plus 3K. If I have a more than one torque, remember, torque, just like force, it's an analogy, it does obey the law of superposition. So I can add up all of my torques to get a total torque, as long as I'm keeping my I, my J, my K notation, only adding up my I directions, my K directions, and my J directions, not in order. So I began to build this whole language. We have our language of translational motion, force, mass, acceleration, velocity, and distance. Well, we have our rotational analogies. We have torque is a force, moment of inertia, I is our mass, alpha is our rotational acceleration. We have a rotational velocity, we have a rotational displacement in theta. So if we have all of those things, we also have momentum. We know linear momentum, mass times velocity. Thus, we also must have some rotational concept of that, of angular momentum. Angular momentum is just our capital letter L, and we're bringing in the exact same values. I is our analogy for mass. Omega is our analogy for rotational velocity. Nothing new here, just kind of looks a little different. So what is linear momentum? What is angular momentum? We know Newton's laws, and we know Newton's laws is really just a momentum law. And momentum we have defined before as an object's ability to remain in motion. Very simplistically, it is moving inertia. Well, I know that technically the net force acting on a body, it's a time, rate, and change of its linear momentum. That's where our Newton's law takes place. We can take all of these words and make them completely analogous to torque, right? We know there's a rotational motion. If I apply a force to a rigid body, I can get it to rotate. That torque causes some angular momentum. Why? Because force causes momentum. A torque causes an angular momentum. That only makes sense. So we can see a little bit of calculus. Force is really our change in momentum per unit time, which means torque is our change in momentum per unit time. We know that torque and angular momentum have to be measured from the same axis point. In other words, I don't want two different axes. That doesn't work. And it gets real messy if we're in an accelerating reference frame. So we say it must be an inertial reference frame. Here's a very simple derivation to get from our from our torque all the way down to our torque equation of R cross F. Just some simple bullet points. Again, we're using our translational motion as a map for our rotational motion. I know my change in momentum per unit time. This is just my cross product. This is my definition of momentum at a distance, at some radius away. I know I have angular momentum. I know momentum is mass times velocity. I can pull up my mass as a constant. And now I'm taking a derivative. It's a calculus rule. It's the chain rule. I'm expanding through that. You can see here I have V cross V. Well, those are in the same direction. That's just going to equal 1. All the way going through. This shows a simple, or a doable, I should say, derivation of where torque comes from. Torque as a cross product. So now we have some interesting things to talk about. I have angular momentum. Well, let's start with translational momentum. Momentum I know is mass times velocity. Well, if I take that point all the way at the end of some rotation or some distance away, some r, I know that momentum is just an object's mass times velocity. Well, if the momentum at that distance r is an angular momentum, right? I know there are, again, two sides to every equation. Angular momentum is just its momentum at some distance away. Angular momentum is also I times omega, which means I can set r cross p equal to I times omega. Let's look at a couple of examples. First, the simplest example, the angular momentum, senior moment, the angular momentum of some point particle at some distance r away. Well, this is starting to bring in everything we know now. I know that the moment of inertia I of some particle, some distance r away, is just mr squared. Well, angular momentum, L, is equal to I times omega. I is equal to mr squared, and I know omega, I can get a translational velocity out there of v over r. My r's cancel. I have the moment of inertia, the angular momentum, L, of some point mass at any distance away is its mass times its velocity times how far it is. Nice and simple. Well, what if I have a real life problem like a fan or a propeller, a helicopter propeller in this case? How do I do this? What if I want to find the angular momentum of this entire object? In other words, what's going to make that object keep rotating because I want my helicopter to fly? So things I'm going to look for here, one, the torque or that twisty force produced by the motor, and two, how fast at the very end, obviously, because the velocity here is faster than the velocity in the middle. So I want to know how fast the end of those blades are turning. Be sure to read through this question, and as always, please take a pause and try and go through the whole thing. What do I know about this? Well, if I look, I can kind of see that I have three rods, and I have a rod of mass m, some distance away. I know they are all identical, which means if I know about one, I can add them all up, because remember, torque is obeys the law of superposition. So I'm going to try and find the force. It's twisting around. I can't find the force. Quick review, F equals ma. I know mass is a change in velocity per unit time. I know m times v is momentum, so my force is a change in momentum per unit time, which means my torque is a change in angular momentum per unit time. So what do I know about that? I know L is equal to I times omega. And right now I'm only concentrating on one of them. So if I know one and they're all identical, I can do them all. So I know the angular momentum of one of them. L equals I times omega. I can look up the fact that my moment of inertia, I, for a long, thin rod rotating about an axis is 1/3 ml squared. Throw that into my angular momentum equation. I have 1/3 ml squared, and there are three blades. 3 times 1/3 ml squared times my rotational velocity, omega. That was given to me in the problem. I can find my angular momentum of 165,240 kilogram meter squared per second. I know that every blade started from rest. Thus, I know that that is my change in angular momentum. Then I can find the torque. Torque is just my angular momentum divided by time, and I get 1,377 Newton times meters. Now, I want to be careful, and I want to point out again that a Newton meter is the same unit as energy, but torque is not energy. Please don't forget that. Last, I can find the velocity just by simple plug and chug. The last example is the most difficult example. I know we've run a little long here, so I hope you're still with me. Here I have a child on a merry-go-round, and that child is way out here, 2.5 meters away from the center. Merry-go-round is spinning around in circles. We're going to assume the merry-go-round is uniform cylinder. What's going to happen? I want to know what is going to happen to the velocity of this merry-go-round as this kid gets real excited and runs towards the center of the merry-go-round. So the merry-go-round is spinning around, spinning around, spinning around, and he's going to make a break for that center. This is a total conservation problem. Conservation of angular momentum happens just like conservation of linear momentum happens. So What does that mean about everything that I got going on? First of all, you have to think to yourself, if that kid is in the center, he's got no more angular momentum. Why not? He's got no more angular momentum because his radius is 0. So he's no longer moving at some distance away. That becomes really important. I'm going to solve conservation of momentum like I've always solved before. My momentum before equals my momentum after. In other words, the momentum of this whole disk with him running around, with him stationary 2.5 meters away of the disk plus the child is the same as just the disk when he's in the center. So I have the moment of inertia I of the disk plus the moment of inertia of the child and the angular velocity of both of them. This is just momentum before equals momentum after. So what are all the things I got going? First of all, I can totally keep my RPMs in RPMs. It doesn't actually matter. I wasn't specific. If I needed to get into radians per second, that's something I'm sure we can do. So I got the moment of inertia I of my disk, 1/2 mr squared. I can look that up. I've got my angular velocity of the child initial, plus the moment of inertia. I'm going to treat this child, if you notice, mr squared. I'm going to treat that child as a point particle because they're a point particle as compared to the giant disk. That will work totally fine. So I've got my point particle and their angular velocity as well, their omega I, equals 1/2 mass of the disk times the radius of the disk. And now it's just the final velocity of that disk. Well, this point particle, omega I, notice those two things should be the same because that point particle is rotating on the disk. Plug in my numbers. I know my omega I of the child, omega I of the disk are the same. I knew the moment of inertia I of the disk. I know the moment of inertia of my point particle. It should be a simple plug and chug understanding. Conservation of angular momentum is just like conservation of linear momentum. We've not changed any physics. We've just complicated it a little bit because now we've got this rotational motion. You should get a final velocity of the disk of 5.1 RPMs. And that makes sense if momentum is conserved. The disk should go faster because the kid's mass doesn't count anymore. The kid's standing in the center of it. No more angular momentum for them. That's all I have for you today. Again, I apologize for going over so much, but there was a lot of twisting and turning, physics jokes. Please feel free to like, comment, and subscribe, and I will see you folks next time.